Gas laws. Okay, so reviewing some of people that actually could pull up the simulation. How would you describe the activity of the gas particles in the container? Anyone? No? No one wants to speak up? How were they moving? What did they look like? What were their behavior?
They were going in many different directions.
Random.
Yes, they were
colliding off of each other and bouncing off
the walls.
Good. They were bouncing off the walls, colliding with each other, moving in straight lines. I heard that back there. Kind of random, but bouncing, knocking, hitting the walls. Those are all good descriptions of what was happening. But if you only had like one of those tiny little light species in there, that red gas particle, how would you say the volume of the one gas particle would compare to the entire container? Is the volume large, small in comparison to the container? One little gas tiny particle in that big box. Small. Yes, that's what we're going for. And the volume of each gas particle is considered so small that we do say that they are negligible in their volume. The individual particles themselves. What happens when the gas particles collide with each other and the walls?
They change directions.
They do change directions. Do they also change speed? Very good. Anything else you saw? Okay. And what happens to the movement of the gas particles as the temperature was increased?
Speed up.
They definitely moved faster. Yes, they would. And what would happen when you would just add a lot more particles to the container? A lot more gas particles.
Because the container might increase.
Well, yes, if you didn't set the volume to stay constant, it would probably increase. The pressure also increased. Why would the pressure increase? More collisions with what? Particles with the walls of the container, because that's what actually creates the pressure, is hitting the walls of the container, the frequency of those collisions. Very good. So, here we go. Gases expand and compress to fill any container. They are in random motion, and we say there aren't really any attractive forces between the particles or repulsive forces. And each individual particle has no volume. It's negligible in comparison to that big, huge space that it is in. Lots of empty space. But we do measure the volume of the gas, but we do it based off of the container that it's in. So we will be figuring out the volume based off of the size of the container that it's occupying, since it does fill the space completely. All gases exert pressure. Why? Because they're going to bounce off the walls of the container. Of course they are. And the pressure of the gas is caused by the collisions of molecules with the walls and each other. Magnitude of the pressure is related to how often and how hard the molecules strike the walls and each other. So yes, it's a little bit more power, but as you speed them up, they hit the walls more frequently. The frequency of collisions with the walls, of course, also is part of increasing that pressure. Now, kinetic molecular theory describes the behavior of gases. Gases are so small, we say that they are negligible. And compared to the average distance between them, that goes with the idea that they don't really occupy any volume as individual gas particles. Molecules move randomly in straight lines in all directions, so they're not wavy lines. They go in straight line directions, various speeds. Forces of attraction or repulsion between them are weak or negligible, so there aren't any intermolecular forces between them, nor are there any repulsive forces. So no London dispersion, dipole-dipole, or hydrogen bonding. Okay, they collide, they bounce right off, because every collision is considered to be perfectly elastic. Does everybody understand what a perfectly elastic collision is? Basically, when they collide, the kinetic energy is transferred. There is no actual loss of energy. Last but not least, the average kinetic energy is actually the measure of temperature. It is directly proportional to the temperature. What you should realize about the average kinetic energy, it is a measure of an average. Some gas particles, like you saw, were moving more slowly. Some were moving very fast. So they take the average of the speeds, and that correlates to the temperature amount. So it is proportional. Okay, so as temperature increases, the kinetic energy is going to increase. Okay, any question on the basic definitions of the kinetic molecular theory? Because now we're going to start doing those equation maths. Yes?
So do the particles actually transfer energy to each other, or is it like in an ideal scenario are all particles equal small energy?
Yes, yes, because that would be complete no loss of energy in the collisions of the particles.
Is that what makes them elastic, or is that just a side effect?
Well, once again, we're also under the notion that there are no attractive or repulsive forces. So in an ideal gas, it would be perfectly elastic collisions. Sometimes gases don't behave ideally, though. So then those forces of repulsion and attraction do kind of play a role. We don't get to that level here. We do that in AP, but so for your purposes for this year, we just really need to focus on understanding that these are the postulates of the kinetic molecular theory, and that we're saying the gases, when they are ideal, they're going to be behaving this way. Okay? Collisions, okay? Bump into each other, go a different direction, form a straight line. The elastic versus the inelastic collision, pow, and then you have the same amount of energy transferred, moves along. Whereas here, if you want to see the inelastic one, where it hits it, but it doesn't necessarily move at the same speed or have the same amount of energy anymore. So we're assuming the elastic collision is what is taking place. Like I said, though, when they're not behaving ideally, they don't always have that. So units, though, these are the three pressure units you have to know for standard pressure. Does anybody remember what standard pressure means? The pressure of the atmosphere when you're standing at sea level, yes. So there's 3 of them that you have to have memorized. You have to know 1 ATM, which is 1 atmosphere. Now the 760 belongs to the measurement torr and millimeters of mercury, but they are the same measurement. Torr is after the guy's last name. Millimeters of mercury is actually his apparatus that he used and developed. So the 760 number belongs to both, and they are the same thing virtually, because it's the person and his apparatus. One's millimeters of mercury, another one's torr after his last name. 101.3 kPa, the kilopascals, that one is also important, and we use that one as well. These are the 3 standard pressures, because in problems they're going to refer to standard pressure as your pressure, and they're not going to give you the numerical values. So you have to have these ones memorized to insert and use as needed. Okay? Liters, be able to convert liters and milliliters. It's going to be similar to your molarity dilution equations, where in the molarity equation it always has to be in liters. The dilution equation, though, you can use milliliters on both sides, that's okay. Here we have a bunch of gas laws where you can use milliliters on both sides. However, there is one particular gas law where it has to be in liters, that's the ideal gas law. That equation, you must have it in liters, so if they do give you milliliters, you must convert. Remember, you're dividing by 1,000, so really all you have to do is move it 3 decimal places to the left. Good? Now for temperature. Temperature is very important. All gas laws. Do not pass go, do not collect $200, do not do any of that until you change your temperature to Kelvin. So, the temperature Kelvin, why is it important? This is the metric system scale. Of course, we don't really use it other than science, but why is it so important? It's because the entire scale for Kelvin is all positive values. 0K is what we know as absolute zero. Does anybody know what that actually means? Yes?
It means that theoretically all the particles at that temperature have no energy to stop moving.
There is no movement, no energy at absolute zero. Exactly. But on the Kelvin scale, there are no negative temperatures. Celsius and Fahrenheit both have negative temperatures. If you try to use them in the gas laws, then you might get negative volumes or negative pressures, which just frankly aren't reasonable. Okay? So everything has to be changed into Kelvin, into the Kelvin scale. Before you do anything, change your temperatures if they're given to you in Celsius. 2 Kelvin. It's a very easy fix. All you got to do is add 273. That's the magic number, 273. And I will declare to you right now as well that when you add the 273, your new temperature is created, like the 323K here, that has 3 significant figures now. And it is considered to have 3 significant figures. Negative 25 degrees Celsius, add the 273 again, you get 248K, also with 3 significant figures. Any questions on that? All right, off to Boyle's Law, our first one here. Boyle's Law, pressure-volume relationship, P1V1 equals P2V2. That is the only gas law out of the ones up here that has an inverse relationship. What do we know when we say it's an inverse relationship? What does that mean about our pressure and our volume?
When one goes up, the other one goes down.
Yes, they are opposite. If pressure goes up, volume goes down. If volume goes up, pressure goes down. So they form a negative slope, as you can see over here on the graph, the negative slope. But let's also conceptually think about this. We're looking here at 1 atm, our pressure, and we're at 1 liter for our volume. We decrease the volume by a half. Now our particles have a lot less space to operate in, so what are they going to do? They're going to hit the walls more often, therefore increasing our pressure. If we decrease it even more, they have less space to move around, so what are they going to do? There's our volume, it's even 1/4. Now our pressure is increased even more because they're hitting the walls of the container more frequently. Okay? So the one thing you also should note about Boyle's Law is temperature remains constant. Temperature remains constant. It's only pressure and volume that are going to be changing. And this is good equation math, very easy equation math. Let's go over an example here. A helium-filled balloon is released into the sky, and we're assuming at constant temperature. What happens to the volume of the balloon as the balloon goes up? If we're going up in the sky, what's happening to our atmospheric pressure?
There's less pressure.
Yes, there's less pressure up there. So what should be happening to our
The volume.
volume?
Down.
What? Yes, the volume should go up, and the balloon should increase in volume. However, does anybody see a problem with this example?
Temperature varies.
Yes, as the balloon would be going up in our atmosphere, really would the temperature be remaining constant? What do you know about when you go up in a higher...
It's gonna get hot.
It's going to get a lot colder, right? So really, that's a flaw in the example here. We're assuming that temperature is staying constant, but it doesn't. As you go up in the atmosphere, it gets a lot colder. Okay, so next law. So we have Boyle's Law, and yes, these were named after people. Charles' Law. This is the volume-temperature relationship. And it's directly proportional down here, if you can see, directly proportional. Volume and temperature are going to vary. That means pressure is going to be constant. Pressure should be constant. Now, all the rest of them besides Boyle's are going to be direct. So if you remember that Boyle's is the inverse one, then you got the rest of them made. Okay? Anybody not like fractions? Okay, you see the formula is written as proportions or fractions here. I don't like them, so I get rid of the fractions. I cross them up. I cross multiply. V1T2 equals V2T1. If you don't like fractions, do it that way. Memorize it that way. It's a lot easier to operate within in order to do the algebra very quickly. Right? Anybody else agree with me? Yes, you like the no fractions? Okay. So here looking at, this is a conceptual example because some of the gas law problems, there's usually 2 or 3 on the SOL. Some of them have numbers. Some of them will just ask you a conceptual question like this one. A basketball is left outside if the temperature drops from 50 to 25. What happens to the volume of the basketball? It should decrease and deflate a little bit. Yes. Good. You see down here, decreased. Very good. Yes, the temperature now, the volume of the gas has condensed a little bit and compressed. Now, before we get to the next gas law, we're going to look at an example real quick. The soda can crush. I'm sure you've probably seen this before, but let's kind of ask ourselves a few questions before we watch the short little video. As the can is heated, what happens to the air and water molecules inside the can? How about when it's placed in the cold water? What happened to the pressure when it was heated and cooled? Inside the can, outside the can, let's try to think of that. What's going on with the pressure? How does the air pressure work on the outside of the can? And what is the relationship ultimately between pressure and temperature? So you're going to watch this short little video watching what's happening, and we're going to try to think about it in terms of gases. So let's discuss. As the can was heated, what happened to the air and water? So they put a little layer of water at the bottom. So as it's heated, what happens to the air? Well, yes, it would spread out, but what's actually going to start filling the can, pushing the air out? A lot of water vapor, a lot of gas molecules, because the water was boiling. You saw the little vapor coming out of the top, right? Now it's filling up with lots of water vapor. Yes, there's probably a little bit of air still in there, but it's filling up. Okay? Then when you place it into the cold water, what happened to it? The can went in and shrunk. So that follows kind of Charles' law, right? The temperature volume thing. We're cooling it down, so the volume should also go down, right? But now let's think about it, about the pressure. Inside the can when it's being heated, what do you think about the pressure? It should be increasing. They're moving faster, right? We're increasing the temperature. When we cool it, though, we have to consider two pressures, the pressure inside the can and the pressure outside the can. That's the atmospheric pressure. So inside the can, when they cool it, what happens to the pressure? The pressure decreases a lot, just like the volume did, right? So yeah, there's still gas particles in there that condense and compress. The atmospheric pressure, though, now is greater than the pressure inside the can, so that also causes the crunch of the crush of the can, because that atmospheric pressure now will push it in. And the gas inside is still inside, because you saw I tipped it over. It's not like the gas escaped through the water or anything. Then the can was crushed because the pressure on the inside went down. So what can we say about pressure and temperature? As you cooled it, what happened to the pressure? It decreased. Thank you. Okay. All right. So that brings us to our last law, Gay-Lussac's law. It's the pressure-temperature relationship. So that means which variable is going to be constant here? Volume. So volume is held constant, and it is also directly proportional. So cross them up if you don't like the fraction. P1 T2 equals P2 T1. And it is also a positive slope or straight line going on there. So volume is constant, pressure and temperature are going to vary. So let's look at a few example problems. Or this example problem. This happened to me actually this winter. What happens to your tire pressure during the winter?
It drops.
It definitely drops. And the sensors in my car went off and said I got down to about 30 PSI, and the car is supposed to be at like 36 PSI. And you want your maximum performance out of your tires, so you got to make sure you maintain that correct pressure. So yes, in the winter time, the pressure decreases. There you go, you have it. All right. Avogadro's law. Now, this one we don't normally calculate a whole lot with, but I do want to describe the relationship for you because conceptually they might ask you a question about it. Volume and moles are directly proportional provided that temperature and pressure are constant. Equal volumes of different gases contain equal number of particles or moles. So, what exactly does this mean? That volume 1 over the mole number of that gas is going to be the same as the volume 2 over the, it's proportional to the moles of the other gas. It's also direct. But in this example here with the balloons, this one's actually showing you 3 different types of gases. So here we have helium, here we have oxygen, and over here we have nitrogen. 3 different gases. They're all at the same temperature and same pressure. They're at 1 atmosphere and 273 K. But they all have 1 mole of gas in them. That means they have 6.02 times 10 to the 23rd particles inside there. So they all have the same number of particles. It doesn't matter if hydrogen's lighter or nitrogen's heavier or helium's lighter. It doesn't really matter. The amount of particles is what's going to control the volume here. Since they all have the same number of particles in there, their volumes are all going to be equal. Okay, so keep that in mind. We don't typically calculate ones with these because usually the mole number stays constant. The number of particles in the gas is not shifting in the problems. Yes? O2 would be the particle. It is the covalently bonded elemental form of oxygen. No, the particle is one entity. So one entity, yes, it can be a compound, it can be just an individual atom to be the gas. Helium, yes, is a monatomic gas, whereas oxygen and nitrogen are diatomic. But they still have the same number of particles if there's 1 mole of that substance, because there would be 6.02 times 10 to the 23rd atoms of helium versus 6.02 times 10 to the 23rd molecules of oxygen and nitrogen. So keep that in mind. Now to help you remember, the P and the V go on the top, the T goes on the bottom in general, but you can cross up the T's. That's what I do to get them out of the denominator. So I want you to go ahead and try to identify the gas, figure out the formula, and set it up real quick. Go ahead, take about 5 minutes to look at these example problems. All right, for this particular one, which gas law are we looking at and why? Boyle's. Why? Because we have 2 volumes, we have a pressure, and what else they tell us? They tell us that the temperature is constant. So we know this belongs to Boyle's. All right, so then we do our P1V1 equals P2V2. So now you have to go through the statement here and pick out your variables. So 4 liters, that's going to be V1, going to 2.5 liters, that should be V2. Then over here, if the pressure of the gas at the 4 liters is 210 kPa, that must be pressure 1. So we are missing pressure 2. That's what we're going to search for here. When you plug in, we get 210 kPa times our 4 liters. That's going to equal our pressure 2 that we do not know, times the volume 2. And what you should notice, if you write it all out, is the liters are going to cancel. And what are we left with? kPa, that's how we get our unit. The liters cancel, and now we're going to get our pressure. How many significant figures should we keep here?
2.
2. All our measured values in the problem are at 2, so we're going to keep 2. And so the 336 that you get in your calculator should turn into a 340 kPa. Did you get that? Very good. Let's move on to the next one. Which gas law are we going to use here? Charles. If you look, we have 2 temperatures. We have a volume, and then it tells us too that the pressure is constant. Pressure is constant. So yes, this is going to be a Charles law problem. Before I do anything else, what should I immediately do?
Celsius
Exactly, I should change my temperatures to Kelvin. Do not forget to do that immediately. So we add 273, this becomes 313 K. We add 273 and this becomes 348 K. You cannot use the equation unless it's in Kelvin, so make sure that you do that first. Then we have our V1 T1 over T1, excuse me, equals V2 T2. I'm going to cross them up. I'm going to make mine be V1 T2 equals V2 T1. Then I'm going to read through here, this must be T1. And it has a volume of 232, so this is going to be V1. If the temperature is raised, so this is now T2, what is the new volume? So I'm missing V2. That's going to be what I'm searching for. So now I plug it in and I calculate. So V1, 232 milliliters, times my temperature 2 over here, 348 K, equals V2, that's the variable I'm searching for and calculating for, and then my temperature 1 is 313 K. Now, V2, how many sig figs are we going to keep?
3.
All of them have 3, so yes, we will keep 3. Also, remember this is basic algebra here. You're going to multiply these two numbers and then divide by the 313, just like you would in algebra. Multiply the left, divide by the right to get your V2 all by itself. And did you get 258 milliliters? Then you are good. Let's look at the next one. Sample of neon is at 89 degrees Celsius and standard pressure. If the pressure changes to 145 kPa and the volume remains constant, find the new temperature. Whose law? Gay-Lussac's. Yes, very good. This is a pressure temperature thing. Now, what should I do immediately? Change this to Kelvin. So it's going to be 362 K. Now, there is one other little glitch here. Volume is constant, that's good, but it tells us this is temperature 1, but here is our first pressure, which is standard pressure. Which standard pressure do I need to remember to choose then? My other pressure is 145 kilopascals. So what should I choose as my standard pressure? Yes, so pressure 1 then needs to be 101.3 kPa. My second pressure here is the other one, 145. I'm looking for the second temperature. So T1, T1, P2, T2. Cross them up, P1, T2, P2, T1. There we have it. Now we can plug everything in. Pressure 1, 101.3 kPa times our second temperature, which we don't know, so that's going to stay the variable. And then our second pressure, 145 kPa, times the first temperature, 362 K. Now, of course, the kPa's will cancel, but my pressure goes from about 101 to 145. So what should I be looking for in my temperature value? So that I can visually kind of see that I know I'm getting it right. My first temperature is 362 K, so my second temperature should be what? If my pressure is increasing, my temperature should be at least above the 362 mark, right? Should be larger, because that's the way the relationship, the direct relationship works. So, do we get a larger temperature? Yes. We get 518 K. Now, this is the extra little added step. Since they gave us the temperature in Celsius, we need to convert it back to Celsius. So subtract 273 and you get 245 degrees. Right? Does that make sense? Alrighty.
Shouldn't the